Dear Professor and faculty member, my name is Sukma.meganova FND. I'm a doctoral student in Rajamangala University of Technology, Tanyaburi. I want to present my homework about proportional, integral, and derivative controller. This is the introduction. A system consists of three elements, which is input, process, output, as shown in this block diagram. The signals flow from the input through the system or process and produce an output. The system is an interconnection of elements and devices for a desired purpose. And the control system is an interconnection of components forming a system configuration that will provide a desired response or a system that provides an output or response for a given input. And then the process is a device, plan, or system under control. The input and output relationship represents the cause and effect relationship of the process. There is a block diagram in here. The input will usually be an ideal form of the output. In the other words, the input is really what we want the output to be. It's the desired output. The output of the system has to be measured. In this video, we show the system we are trying to control the plant and a sensor that measures what the control system is doing. The input to the plant is usually called the control effort, and the output of the sensor is usually called measured output, like in this block diagram. This is the general block diagram of control system. There is an input or reference value that flows to the input transducer and then flows to the comparator. This is the summing junction from the output of the sensor and compared to the input and then produce an error or actuating signal, then flows to the controller to minimize the error. And then there is a summing junction here because sometimes there is a manipulated in here. And then give to the process or plan, then flows to the summing junction again if there is a disturbance, and then produce an output or control variable. And then from the output or control variable, then feedback to the comparator. This is from the sensor, measure the output, and feedback to the summing junction or comparator. Here to compare with the input, then produce an error, and then after that the controller will minimize again the error, flows to the plan after the manipulated in the summing junction here, and then from the plan then sum with the disturbance if there is a disturbance, and then produce an output, and then close cycling like this until the output is same with the input. Then the meaning of the part in this block diagram from the input. Input is a desired response. Output is actual response. Control variable is the quantity or condition that is measured and controlled, normally in the output. And manipulated variable, the quantity or condition that is varied by the controller to adjust the control variable. Disturbance is signal that affect the value of the output. Then the controller is measuring the control variable and applying the manipulated variable to correct deviation of the measured value output from the desired value input. Then the summing junction or point is to represent addition or subtraction of signal. Incoming signal lines either plus addition or minus subtraction sign. The output signal is shown with an outgoing arrow. There is two types of control system. The first is open loop. This is the block diagram of open loop system. There is no feedback here. The open loop is any physical system which does not automatically correct the variation in its output because there is no feedback here. This is the input flows to the controller and then the signal flows to the plant and then produce an output. And then the second is a closed loop or feedback control system. This is the block diagram of the closed loop control system. The important thing is there is a feedback mechanism here. The closed loop or feedback control system, the system in which the output has an effect upon the input quantity. It utilizes feedback to compare the actual output to the desired output response. So in this block diagram, there is an input or desired output response. Then the signal flows to the comparison. This is for compare the measurement or the sensor with the desired output or input. Then flows to the controller and then flows to the plan or process, then produce an output, and then from the output from using the sensor, this is measure the actual output, then compare to the input, and produce an error, go to the controller again, and then go to the plan, and produce output, and then feedback again, compare with the input, and cycling like that until the actual output is same with the desired output. In a closed-loop control system, both linear and rotational motion systems are adjusted using feedback mechanism to ensure the output follows a specified preference, whether for position, speed, or torque. This is the PID controller. This is a block diagram of the PID controller. P stands for proportional, I stands for integral, and D stands for derivative. The PID controller determines how much and how quickly correction is applied by using varying amounts of proportional, integral, and derivative action. This is the block diagram of unitive feedback system. This is the input with symbol R, and then this is the comparator, comparison process from the feedback with the input, and then this is the error signal with some symbol E, and this is the controller with the symbol C in S domain or Laplace domain, and then this is the U output of the controller, and then this is the plan in P in S Laplace domain, and this is Y is the output, and this is the feedback. Inside the controller is shown like in this block diagram. This is the P controller, I controller, D controller. And then from the each controller, then sum all the controller here to get the output of the controller. From this block diagram, we can see in here the output of PID controller, which is equal to the control input to the plan, is calculated in the time domain from the back arrow as follows like this. This is the control signal or output of the controller at time t is equals to proportional gain times to the error at time t plus integral gain times to the integrate the error over time and then plus with derivative gain times to the rate of change of the error. And then we can see in here from this block diagram, the R is the desired output, and then the Y is actual output, and then E is tracking error, the difference between the desired output R and the actual output Y, and then U is the control signal, and then this is a proportional gain, this is integral gain, and this is derivative gain. So from this PID controller, the error signal E is fed to the PID controller, and the controller computes both the derivative and the integral of this error signal with respect to time. The control signal U to the plan is equal to the proportional gain times the magnitude of the error plus the integral gain times the integral of the error plus derivative gain times the derivative of error. This control signal U is fed to the plan and the new output is obtained. The new output Y is then fed back and compared to the reference to find the new error signal E. The controller takes this new error signal and computes an update of the control input. This process continues while the controller is in effect. The transfer function of PID controller is found by taking the Laplace transform is shown in here. This is represents the transfer function of PID controller. This is the ratio of input error and output control signal in frequency domain is equals to proportional gain plus S times derivative gain times integral gain divided by S. Then is equal to derivative gain times 2S squared plus proportional gain times 2S plus integral gain divided to S. The characteristic of the P, I, and D terms is increasing the proportional gain has the effect of proportional increasing the control signal for the same level of error. And then the fact that the controller will push harder for a given level of error tends to cause a closed-loop system to react more quickly, but also to overshoot more. Another effect of increasing proportional gain is that it tends to reduce but not eliminate the steady state error. And then the characteristic of derivative, the addition of derivative term to the controller adds the ability of the controller to anticipate error. With simple proportional control, if proportional gain is fixed, the only way that the control will increase is if the error increases. With derivative control, the control signal can become large if the error begins sloping upward, even while the magnitude of the error is still relatively small. This anticipation tends to add damping to the system, thereby decreasing overshoot. The addition of the derivative term, however, has no effect on steady-state error. Then the characteristic of integral gain, the addition of an integral term to the controller tends to help reduce steady-state error. If there is a persistent steady-state error, the integrator builds and builds, thereby increasing the control signal and driving the error down. A drawback of the integral term, however, is that it can make the system more sluggish and oscillatory, since when the error signal changes sign, it may take a while for the integrator to unwind. The general effects of each controller parameter, from proportional gain, integral gain, and derivative gain on a closed loop system are summarized in this table. This is for the closed loop response with increasing the PID gain. For the rise time, if the proportional gain is increased, the rise time will decrease, overshoot will increase, settling time will be small change, and then the steady state error will decrease. And increasing the integral gain, the rise time will decrease, overshoot will increase, then settling time will increase, and then the steady state error will decrease. And then increasing the derivative gain, the rise time is small change, and then overshoot will decrease, settling time will decrease, and steady state error is there is no change. This is the PID step response because from the previous slide there is a rise time, settling time, steady state error. So we have to know what is the meaning of that characteristic. The PID step response, the response is quantified by measuring defined waveform characteristic. From the rise time in here, rise time is the amount of time the system takes to go from 10% to 9% of steady state error or final value. Then percent overshoot is the amount that the process variable overshoot the final value expressed as a percentage of the final value. Then the settling time, this is the settling time, is the time required for the process variable to settle to within a certain percentage commonly 5% of the final value. And then the steady state error is the final difference between the process variable and set point. Then the peak time is defined as the time the system takes to reach maximum overshoot. And then there is a dead time. Dead time is a delay between when a process variable changes and when that change can be observed. And then the set point is here, is desired output value or the value for a process variable that is desired to be maintained. This is the example of the step response of closed loop control system. There are three response in here. In the red line, this is the underdamped response. This is with the theta or damping ratio is less than 1. You can see here that still there is small oscillation. And then in the green line, this is the critically damped response with theta is equal to 1. And then for this yellow line in here, this is for the overdamped response. This is the theta is more than 1. From this response, we can see the meaning of the overdamp. The system returns to equilibrium without oscillation. And then for the critically damped is the system returns to equilibrium as quickly as possible without oscillating. And then the underdamped, this is the system oscillates at reduced frequency compared to undamped case, with the amplitude gradually decreasing to 0. And there is one more response. This is undamped, that's not shown in this picture. Undamped is the system oscillates at its natural resonant frequency. This is the response oscillates from the start until the end of the system is stopped. And then this is example of PID in linear plan. This is use mass spring damper system. This is the block diagram of the mass spring damper system. From the input, there is an input flows to the comparator. This is compared with the feedback unit. Then produce an error signal that gives to the controller unit, and then output the control unit give to the mass spring damper plant, and then from the output of this plant then go to the position sensor and then produce an output. Then from the output measured and then use feedback unit here to compare with the input and produce an error, and then from close to the controller unit, then for minimize the error, go again until produce the output, cycling more and more, then until the output is same with the input. And then this is the mass spring damper system. There is a mass in here with symbol M, and then there is a damping coefficient with symbol B, and then there is spring constant with symbol K, and there is a displacement with the symbol is X, and there is a force with the symbol is F. So from this system, we can see the equation in every system in the mass is F is equal to m times to a, or a is the acceleration, is equal to m times x double dot. And for the spring system, the force F is equal to k times to x. This is same with the velocity. Oh, I'm sorry. And for k times to x, and this is for damper system, the force F is equal to b times to v, v is velocity, is equal to b times to x single dot. In this mass spring damper system is consist with one damper, one spring, one mass, and one actuator. And then this is the free body diagram of mass spring damper system. From this free body diagram, with summing the force and apply Newton's second law, the equation will be like this: F minus B times x single dot minus K times X is equal to M times 2x double dot. And then the governing equation of this system from this equation can be changed into like this, because we have to know the input and output equation. This is for the input equation. This is F is equal to m times to x double dot plus b times to x single dot plus k times to x. And then by taking the Laplace transform of the governing equation, the f is equal to m times s squared x plus b times s times x plus k times x is same with f is equal to s times with m times s squared plus b times s plus k. And then the transfer function between the input force F and the output displacement x then becomes 1 divided by m times s squared plus b times s plus k. Because if we give the force in here, force is the input, then this my spring damper system will move, and the different position from start to the end position produce the displacement. The symbol is x. So this is the output of the mass spring damper system. Then by using the example from this website, then I use the parameter value for MSD, or mass spring damper system, with M is 1 kilo, B is 10, and K is 20, F is 1. Then after made the MATLAB code here like this. This is the transfer function and this is the controller, and then show the response, step response, and then this is the value of PID that used in here. Then just process the PID controller using function of PID, and then calculate the feedback. Then this is for the time for the step response, and then we can see in here this is the step response of this controller. And then this is the result after using the PID tuner in MATLAB. That continue from the previous slide, the code in previous slide, and then give the function PID tuner of the controller P. Then the result will shown like this. And then just pick the show parameters, and then we can see here there is a controller parameter, there is proportional gain, integral gain, and derivative gain. And then we can see the performance and robustness in here: rise time, settling time, overshoot, peak, gain margin, phase margin, and closed loop stability. And then after dragging the response time slider here to the right to 0.14 seconds, this is caused the response to indeed speed up, and we can see the proportional gain is now closer to the manually chosen value. We can also see the other performance and robustness parameter for the system. I'm sorry. Note that before we adjusted the slider, the target phase margin was 60 degrees. This is the default for the PID tuner, and generally provides a good balance between robustness and performance. And then by specifying the previously designed or baseline controller C as the second parameter, PID tuner will design another PID controller instead of P or PI, and will compare the response of the system with the automated controller with that of the baseline. Then from the previous code, just write again PID tuner P and C. Then we can see here, this is the result. We can see in the output window that the automated controller responds slower and exhibits more overshoot than the baseline. Now we can choose in the domain. This is changed to frequency option from the to strip, which reveals frequency domain tuning parameter. We can tuning this parameter, and then we can see here there is two response in here. This is in the continuous line in here. There is an overshoot, but from the baseline response here, we can see in the line like this. So we can compare the response, the performance, and robustness in here. So this is all my explanation about PID controller. Thank you for watching.